Wow. Okay. So good afternoon, everyone. My name is Khalid Salama. I'm the co-chair of the WEP for this year with Professor Naveen Khashab, and we're very excited to have you here. We're also very excited to have a lot of out-of-kingdom visitors. We're always excited to have more people attending our events and sharing their knowledge and questions. So please don't feel shy asking questions at the end. We like it this way. So it's my honor and privilege to introduce Dr. Hussam Zawawi. Hussam Zawawi is a Saudi scientist. He's a microbiologist, but in my view, he's doing something more interesting than biology, which is being a cave explorer. He goes around the world exploring caves and finding superbugs and microbes. Now, I asked him, why do you have to do that? I mean, like, we are dealing with lots of microbes in our life. Why do we have to go inside caves and find microbes that haven't been around people? But he thinks it's fun. He's going to convince us it's fun. He's going to convince us that we can actually fight them and we can actually win this fight. Another thing that would be interesting to know, that he has a major award from Rolex. And I'm like, what does Rolex have to do with anything? Rolex, for those who know, is a watch company, one of the biggest watch companies, but he has an award because they have a vested interest in supporting young scientists all over the world. Hussam is also an honorary fellow at Queensland University, where he did most of his education and studies. And I asked him, what's something different about you and you like a lot? And he mentioned polo. So we have our first polo player here giving us a talk at CAUS. So with that, I'd like to invite Hussam to join us and give us a brief history of bugs and superbugs.
Thank you, Professor Salama. Thank you, Professor Khashab. And I thank the organizing committee for having me here. It's such a great pleasure to stand in front of you here this afternoon and present my talk. I love this paint. Unfortunately, it's a dark one because it represents the dark history that has occurred in Europe and different parts of the world, where death was caused mainly by infectious diseases. And if you can see around the picture, for example, on the very right-hand corner of the picture, there's a very brave knight who is holding his sword, hoping to combat death. And on the very left corner is a dying king, alongside other poor and animals who have actually died or dying out of the epidemics. And that, unfortunately, was the reality. Infectious diseases could not really differentiate between wealthy, royal, or a brave knight. And it very much believed that the reason for this is actually miasma. And the translation for miasma is actually the bad air. And people really did not know what was the cause for causing such a mortality. And one of the very intelligent physicians at the time was Charles Delamore, who was actually a very renowned physician, being a physician for being the personal physician for 3 consecutive kings in France. And he came up with a very ingenious idea at the time, what was the medico della peste, and that is the plague doctor. And it's basically the costume. Probably if you have visited Venice or part of Italy, you would have recognized the beacon mask. And that was a way to try and neutralize the miasma or the bad air, is to stuff the beacon with herbs to provide a nice scent. And that, he presumed, it would neutralize the bad air, as well as the gown, to protect himself as well as the physicians. And that costume was actually highly used by doctors who were trying to help to prevent the spread of plague in Europe. Unfortunately, during that era, a huge mortality has occurred among the physicians who were wearing this costume, and basically because it really did not protect them. And that has continued until the 19th century, and there's a very famous outbreak back in Hong Kong. And that outbreak was very important in the history of plague, because it was at the time where a very famous scientist of the name of Louis Pasteur has actually dispatched one of his trainees, Dr. Yersin, Alexander Yersin, to go and study this unknown outbreak. And one of the activities that Yarsin has undertaken is actually he started to dissect the died individuals. And he was able to see under the microscope an object which looked quite weird. And there's a heavy load of them, particularly in the lymph nodes. And that was actually the birth of the Yersinia pestis, the bacteria that has caused plague. And that has completely changed our understanding of infectious diseases and plague at the time. But later on, in different parts of Europe, as well as in Sydney, there was quite a large outbreak of plague. And one of the things that Yarsin has noticed is the number of rats that were dying on the street. And the very famous medical officer, as well as a military officer, Dr. Simon, conducted a very famous experiment where he had two kinds of rats, one of those who appeared to be sick, and other group of rats who were healthy. And then he's just separated them with a mesh. And after a few days, the healthy rats got sick. But he also noticed fleas that were dying inside the cave, or died inside the cave, or the cage. And he actually was able to isolate those fleas and grow the same bacteria that he observed in the patients. And that was actually the birth of how Yersinia pestis was actually known to spread from one patient to another. Now we have a full understanding of how infectious diseases, or particularly plague in this context, can spread from one patient to another. Another very famous story is actually cholera. And Jon Snow, of course, this is not Jon Snow I'm referring to, but this Jon Snow. Jon Snow, the father of the science epidemiology, which is the science that he invented, really, by studying how patients that, where the patients that have presented with symptoms of cholera have actually were located in the city of London. And by mapping the cases of cholera, it was easy for him to hypothesize that one of the reasons for this symptom was actually due to the ingestion of either contaminated food or water, and he started to conduct a surveillance where he went and asked each of the households what they got exposed to before developing the infection. And one of the famous actions he did in public health was actually taking off the handle of the water pump, and that has prevented the spread of the outbreak, because people were not really exposed to that particular water source, which was actually contaminated by water. Another pioneer in the history of medicine is Sir Alexander Fleming, who was very famous for discovering penicillin. This is a famous picture of his petri dish, which demonstrate doesn't have any pointer, but it demonstrates the colonies of penicillium, the fungus that produces penicillin, and how it actually has inhibited the growth of the bacteria Staphylococcus aureus on the petri dish. And that has happened just by coincidence. And with the help of his Aussie fellow, Sir Howard Florey, they were able to produce penicillin to be utilized in medicine. Why I'm telling you this history? Because these pioneers have demonstrated the way how modern medicine has evolved and has expanded our understanding of infectious diseases. The number of people who are living today, it is believed that is greater than the entire humanity that has ever lived. And the modern medicine that I just narrated part of it in this talk has actually significantly contributed to the significant reduction in infectious diseases, particularly during the last 100 years or so. And this paper that was published in JAMA demonstrated significant reduction in infectious diseases during just a few decades. This is another figure that shows the significant reduction in the mortality and a significant increase in the survival of pneumococcal pneumonia with bloodstream infection, just because of penicillin. Unfortunately, however, we are moving into an era where antibiotics or bacteria are becoming resistant to first-line, second-line, and even last-line antibiotics. And they are becoming multi-drug resistant and sometimes extensively drug resistant, and unfortunately, more and more of pan-drug resistant, which means they are resistant to all available antibiotics. And this is an example of one of the isolates that we have managed to isolate, and I will talk about them later on down the track. That was not a surprise for Sir Alexander Fleming, because during his Nobel Prize speech, he said, and here I quote, "It is not difficult to make microbes resistant to penicillin in the laboratory by exposing them to concentrations not sufficient to kill them. And the same thing has occasionally happened in the body." And this is the reality, because that's what we are observing on a daily basis with antimicrobial resistance. So I can say without doubt that antimicrobial resistance is the world's greatest threat at this point of time and in the future. And the reason for this threat is actually because we ourselves have positioned ourselves in a very awkward position. Modern medicine, which we all are dependent on nowadays, is highly dependent on antibiotics. Antibiotics has actually significantly reduced childhood mortalities, as well as women after they give birth, and has empowered the science of transplantation. And unfortunately, because of antimicrobial resistance, and the threat that antimicrobial resistance can have, not only by direct infection, but also by the association with the threat that it can impose on modern medicine, it is anticipated that in the very near 2050, about 10 million cases will die annually due to antimicrobial resistance. It is very unique. Why is that? Because on every paracetamol dose that you consume, or a statin, you have zero effect on the effectiveness of paracetamol or a statin on everybody else. This is not the case of antibiotics. With every dose of antibiotics that we consume for medicinal purposes, or unfortunately that are being misused and being scattered in the environment, there's more and more bacteria that are becoming resistant, and that is not imposing the threat on ourselves only, but also there's a huge and significant threat on everybody else. This very famous quote was said by the former Director General of the WHO, Dr. Margaret Chan, and she said, and here I read, "A post-antibiotic era means, in effect, the end of modern medicine as we know it. Things as common as strep throat or child scratch knee could once again kill." So because of this, myself and many of my colleagues consider antimicrobial resistance as equally important as climate change, because our behavior that in our daily basis, that in the high consumption of carbon dioxide, for example, or production of carbon dioxide, we are impacting the climate change on everybody else. And same happens with antimicrobial resistance. I'll tell you a quick story. In Vietnam, it was actually very known that penicillin, gonorrhea would be easily treated with penicillin. When the US Army has moved to Vietnam, they decided to dispatch the penicillin among all brothel houses in Vietnam to protect the soldiers from acquiring gonorrhea. By the time the US Army has left, gonorrhea was not treatable by penicillin anymore. The same it was. And not only so, but also some of the soldiers who became patients by gonorrhea, they also transmitted gonorrhea back to their home country. Not any kind of gonorrhea, but those that are resistant to penicillin. We have a very similar story that we have observed here in the Gulf countries. By the time, I'll just take you directly to the Bahrain. By the time that third-generation cephalosporin got introduced to Bahrain in the 1988, about 5% of Klebsiella were resistant to that new antibiotics. Just 1 year later, 37%. And the year after, it got doubled. And then due to the implementation of infection control practices and many others, the prevalence has got significantly dropped, and this is still the rate where we are seeing today. There's another story that has been seen by carbapenem-resistant Acinetobacter baumannii, a very famous bacteria for causing hospital-acquired infections. Back in the 1990s, there were a very limited number of states in the United States that have actually witnessed strains of Acinetobacter baumannii being resistant to carbapenems. As we enter the new millennia and the middle of the second decade, more and more up to the level that 60% of Acinetobacter baumannii in some of the states were resistant to carbapenems. And carbapenems, by the way, are a very important group of antibiotics. They are considered the last safe-line antibiotics that we could use to treat these very nasty infections. Again, very similar observation happened here in the Gulf. There are many data that showed back in the 1990s, very limited number of Acinetobacter baumannii, if nearly none, were resistant to carbapenems. As we enter the new millennia, we are seeing an exponential growth of those strains that became resistant to the very superior last-line antibiotics. And unfortunately, there are many resistance mechanisms that have made it through the Arabian Peninsula and have empowered the bacteria to become more and more resistant to antibiotics. I will just walk you through some of the work that we have done, as well as examples, and hopefully I will be able to simplify them so everybody can understand. We have looked at a group of bacteria known as Enterobacteriaceae, which encompasses E. coli as well as Klebsiella. And we looked at carbapenem resistance in them. One of the very important observations, and here I will zoom in, is that we have noticed some of the bacteria were able to spread across patients and cause infections within the same hospital. What does that mean? This is, in another word, it's an outbreak that we could not really recognize. That is demonstrating our deficiency to recognize outbreaks quite quickly, but at the same time, it symbolizes the bacterial ability to spread within patients and cause untreatable infections. Unfortunately, however, that was only the tip of the iceberg, because when we dug deep, we came across bacteria that are resistant to all available antibiotics, or in other words, pan-drug resistant. And it was very smart because it had a lot of different resistance mechanisms, some of them that was developed quite smartly. So probably this figure will try to symbolize what happened. In one of the examples for the reason behind the pan-drug resistance is that the bacteria had made the decision of developing 3 different copies of a very important gene that make the bacteria resistant to one group of antibiotics, which is carbapenems. But that one of those copies was actually placed in a very important position, which made the bacteria resistant to one of the really last-line antibiotics. It's not safe. It's one of the important, it's one of the toxic antibiotics. But in desperate situations, our colleagues, the physicians, tend to use that kind of antibiotics. It's known as colistin. When we discovered this story, we were very proud of this. And we said, well, we're going to start by publishing it in one of the important medical journals. And we started with that journal. Unfortunately, the response came back as such. This is a one-off situation, and particularly the resistance mechanism has occurred in the chromosome. I will explain that a bit later, which means it has a high chance of being able to spread to other species. The reviewer were wrong, because just a few months later, I actually received an email from a colleague in the UAE, and he said, well, Hussam, we saw your recent publication. We actually think that we have the same bacteria, same resistance mechanism, but here in the UAE. And when we started to work with them, unfortunately, we found the same resistance mechanism to ours, but not the same strain, that have made it through different strains across different hospitals in the UAE. And that was frightening, because we really never knew how this new resistance mechanism that we managed to first discover have made it through this way. Probably the next examples will try to simplify the reasons. Similar observation we also found among different bacterial strains in different patients that have a group of genes that make the bacteria resistant to antibiotics and the surrounding environment. So here, probably this example would show that probably there are a group of genes that if they cluster together, they would be able to jump through. There are several hypotheses on how, from one species to another, and also from one patient to another. Similarly, when we conducted the work on the Australasia, we were able actually to isolate a few different bacterial species that very close to each other. They are not really identical, but very close to each other, yet they are from completely different countries. And you know how Australia is. It's a large island that doesn't share any border, land border with any other country. Yet we were able to isolate the same or very close relative of those isolates from Singapore as well as nearby Malaysia. And when we looked at the carbapenem-resistant Acinetobacter baumannii in the Gulf countries, we noticed a very important aspect here. This figure shows, and particularly the red circle, shows identical strains, exactly from the same Acinetobacter baumannii, identical, yet from 3 different countries, from Oman, Saudi Arabia, as well as Kuwait. Same observation again happened with Pseudomonas aeruginosa, where we found a large cluster of isolates that are identical to each other, being resistant to carbapenems. And just recently, we were really bumped by this finding with Professor Anna Payne and his PhD student, who I'm having the honor of co-supervising, Sharif Hala, reported the Saudi first KPC2 that are associated with Klebsiella, one of the Klebsiella species. It's a very important observation. Why is that? Because Saudi Arabia has never seen this resistance mechanism before. And this is the first. Yet, this resistance mechanism has actually caused large outbreaks in New York, in Greece, and in Israel. And never had the chance to cause any infections here in Saudi. So we are really scared that this is probably going to be the beginning of potentially future outbreaks that can occur in the region and can cause severe mortalities. And to be able to understand how the bacteria has the ability to do so, you really need to understand the biology. I don't want to get you through, take you through the detailed biology of the bacteria, but the bacteria has very smart, unique mechanisms that can drive them to become resistant to antibiotics. For example, they can destroy the antibiotic by producing enzymes, or they can change the entrance point to be able to prevent the antibiotics from entering the cells. But uniquely, these resistance mechanisms or these methods that the bacteria can master to pass on to fight down antibiotics, they have the ability to pass on to other generation as well as other bacterial strains, completely different, by what's so-called plasmids. Plasmids are, we can call them as mobile genetic elements that have the ability to spread from one species to another. But there are many other methods that can drive the bacteria to transmit resistance mechanisms, such as transposons, as as much as it was when we discovered a very important resistance mechanism that existed in the region. Remember when I told you about the toxic antibiotic, yet it's the last line true antibiotic. Usually it was also always known to have the ability to spread using the plasmid to other bacterial species. Bacterial ability to drive it to become resistant to colistin, but the significant growth in antimicrobial resistance that correlate with the growth of animal production. And unfortunately, that's an important dilemma because the huge expansion in human population needs to associate with the need to have food security. And one of the methods is what's called the agriculture industry to produce meat. And here is the example is this practice of the agriculture industry to produce meat associated with antibiotics, with more use of antibiotics. I had the pleasure of sitting on a very important high-level meeting where we had discussion with the Deputy Minister of the Environment, Water, and Agriculture here in Saudi Arabia, Dr. Hamad Al-Batchan. And in this paper, there's a very important quote. And this I want to read the bold one. The second is the traditional farming sector, or what's referred to the backyard farming. The traditional sector is a big challenge. I'm referring here to the sheep, animal, and cow with traditional farming, where we are struggling the most. All farm has access to antibiotics and may administer these antibiotics in any form, even in water if they wish to do so. We do not have much control over these practices. This is a huge acknowledgement because here, what he's saying that the 70% portion of the antibiotics, which are utilized in animal, large part of it is actually uncontrolled. And this is scary. Not only so, but also because a lot of antibiotics have actually of medical importance are overlapping with ones that are utilized heavily in the agriculture industry. So there is a huge drive for, unfortunately, more and more development of antimicrobial resistance, which means there's a more and more threat on our lives on a global aspect. So what should we do more? Should we go and discover more antibiotics? Well, in reality, there are more and more evidences show that the new antibiotics that have been discovered and released into the health practice have actually, the bacteria have managed to become resistant to. And this is really scary because it's really a chase-up game. We are trying to catch up with the bacteria that is evolving to become continually antibiotics. Unfortunately, in this video, I'm not the one who's leading. I'm the one who's trying to catch up. And this is the story of my professional life as well, where I'm really trying to catch up with the bacteria that are continually evolving to become antibiotic resistant. A very nice paper that was published a couple of months ago in Nature Microbiology. And here, this quote, I would like to read it all, so please bear patience with me. It reads, and here it says, true multi-drug resistance is a rare phenomena as a proportion of all bacterial infections. Certainly, the value of an antibiotic that will save the patient's life from a multi-drug resistant infection when no other antibiotic will work is extremely high. Yet, the proportion of all bacterial infections that fall in this category is extremely small. That said, the number of bacterial infections that do not respond to any available antibiotics is increasing. Add to this the fact that bacterial infections are acute and of short duration with an early onset of advanced outcome. In this number game, it is difficult for an antibiotic manufacturer to be able to precisely identify the small proportion of the patients who both really need the antibiotics and are willing to pay for the high price of it. So, just to put this into a visual context for you, this is what I have done. These are the, let's presume this blue ball represents the world all infections. This would be the bacterial infections. In this would be the group of infections that would be resistant to the first-line antibiotics, and then this would be the multi-drug resistant ones, and here is the pan-drug resistant one that really need the antibiotics that do not really exist, or we would like to manufacture. So in comparison, unfortunately, despite the fact we extremely need more and more antibiotics, our denominator is extremely high. And this number game has these consequences. In April 2019, a very important pharmaceutical company that developed a new antibiotics has actually filed a bankruptcy because they were not able to justify the very limited sales they have made in 1 year. Again, same happened just last month. Another pharmaceutical company filed a bankruptcy for the same reason. Probably for this reason, it's really important for us to acknowledge that antibiotics are public resources that really need to be maintained and should be treated equally like climate change. Same way how climate change are being managed with global commitment like the Paris Act. Probably with emission taxes like the ones that are being proposed or utilized in climate change. Probably we need to tax for those who are using antibiotics more. Clean and alternative energy, where more and more alternatives for antibiotics, and one of the most important alternatives of antibiotics is actually prevention. If we can reduce the number of infections, we can potentially reduce the need for antibiotics. And consumer education. And I just want to like to take you through quickly our minimal contribution in each of those aspects. So I'm very lucky to have the pleasure of having the chance to see my work being cited or had the chance to sit on committees where we were able to develop policies on a global level, such as those made by the European CDC, as well as by the WHO, alongside the GCC Action Plan to combat antimicrobial resistance, unfortunately, the Saudi Action Plan to combat antimicrobial resistance, and the nearby Oman Action Plan to combat antimicrobial resistance. And probably I will take this chance to encourage all of the scientists here in this room to be part of the policymaking part, because really there's a huge need for scientists to be at policymaking. We understand the science. And if we have the ability to communicate the science in a way that can be understood by the stakeholders, we will have a change that can be made. You already probably know that I'm an avid horse rider. And if you go through the European art, you will realize that fox hunting, a form of horse riding, has always been, the culture of it has always been maintained. Even in the earlier paints, and even in the recent photographs. The costume, the horse breed, the hound breeds, and so on. It's a very maintained culture, and that's how I like to think about microbiology. We as microbiologists are very conservative to maintain the culture of microbiology. We like to grow the bacteria. We like sometimes to sniff and smell the bacterial growth. So those who are laughing are microbiologists, I'm sure. And for those who, and we still like to see the look and the morphology of the bacterial cell under the microscope. And we like to measure and enjoy the growth. But this doesn't help, because the current diagnostic paradigm is really scary. And now I just want to walk you through the process that we conduct to be able to inform our colleagues at the medical wards on how to prescribe antibiotics. So let's presume this patient has, or this neonate would have a bloodstream infection. Then our colleague, the nurse, would withdraw blood from the patient. And then we go and try to isolate the bacteria by growing the blood. And then once the bacterial isolate is isolated, we go after and try to test it against a panel of antibiotics. And whenever that panel of antibiotics give the result after 48 hours or 24 hours, we can go further and test for different resistance mechanisms that can exist using technology known as PCR. And sometimes we go after and do sequencing. In best case scenario, we're talking about 4 to 5 days. And of course, that has a potential to increase the mortality among patients. Rapid identification of has been hypothesized that it will significantly reduce mortality. Unfortunately, the practice that I just narrated is actually enforcing our colleagues, the medical physicians, to prescribe empirical antibiotics. What the word empirical stands for, if you see the word empirical in dictionary, it's actually guessing. We are enforcing our colleagues to guess what is the antibiotics that would be suitable. And the reason behind this is because they cannot really cope with our deficiency as microbiologists and the time that we take to produce results. So there's a huge movement now in clinical microbiology where modern technologies such as MALDI-TOF are being introduced, as well as next-generation sequencing, to help expedite this process. For those who are unaware of MALDI-TOF, it's a matrix assorted laser disruption ionization time of flight mass spectrometry. So it's basically try to measure the bacterial proteomics fingerprints. And according to the masses of the bacterial protein, we would be able to differentiate based on the bacteria. The beauty about this technology, it actually demonstrated it has the ability to reduce the number of, the amount of antibiotics being utilized, which can actually limit the unnecessary use of antibiotics. So what we have done, we have actually managed to use the technology of mass spectrometry to develop a quick method that has the ability to quickly identify more than 200 genes that make the bacteria resistant to antibiotics in 3 to 4 hours, in 1/3 of the cost of the currently available technologies. And when we had head-to-head comparison against the whole genome sequencing, we had 94% sensitivity and as well as 98% sensitivity. So where our technology would sit, probably here, where still we need to grow the bacteria to be able to detect those genes. But what we are hoping to develop is a second generation of this technology, where we're able to directly from patient sample. And that will be a paradigm shift to the current tedious process that I demonstrated. With my PhD student and I at the University of Queensland, we also tapped on a very important methodology using mass spectrometer, where we develop an algorithm for semi-quantitative protein. It's basically the concept goes this way. If the bacteria has the ability to combat antibiotics, then the bacteria will be able to grow, and hence that will correlate with the amount of protein because the bacteria is growing and multiplying. And if the bacteria is dying by the antibiotics, then the amount of protein will remain the same. And our preliminary results are producing something very interesting because we could actually see what we have hypothesized in the results. Another technology that my other PhD student, who was a master's student at the time, Bushra Al-Harbi, is tapping on is near-infrared spectrometry. It was very new to me. A technology that I never done a lot of physics, and basically a tool that has the ability to measure the electromagnetic spectrum. And according to the activity of the chemical compounds in each of the samples, you would be able to differentiate. And we have actually demonstrated the technology's ability to differentiate between 3 bacterial species, Acinetobacter baumannii, E. coli, and Klebsiella pneumoniae. Not only so, but we were very excited to see the ability for the bacteria to differentiate between 2 resistance mechanisms. Another quick technology that we are also tapping on is actually the rapid point-of-care isothermal-based applications, where in less than an hour, we have the ability to extract the DNA, amplify the DNA, as well as to detect it in a lateral flow sample. And our colleague, Joanne MacDonald, has actually demonstrated the technology's ability to develop rapid diagnostics for Ebola, which was actually tested in Africa as well. So with the support of Children's Hospital Foundation in Queensland, my PhD student, Abdurrahman Aifan, and the postdocs are actually helping to develop this technology. But fortunately, on a multiplex level. So hopefully, in the very near future, we'll be able to amplify as well as detect several resistance mechanisms in one shot. For those who are very close in the research environment, you probably will be aware of the blue sky research, which is the ability to conduct research, exploratory research, with no really direct translational outcome. So here is a new term that my colleague and I have came up with. This is dark cave research. Francesco Sauro is a fellow Rolex laureate and a very dear friend of mine. We took the challenge of discovering different caves around the world. The one we have been to in Venezuela was the Imawari Yaute in the Auyan Tepuy mountain. The mountain is very famous for the Angel Waterfall, the highest waterfall in the world. And Francisco and his team were the first in the world to discover that cave. And in the second expedition, I had the pleasure of continuing the exploration, where we went and collected different samples from that cave. And it was really striking to see the untouched, pristine environment that this part of the world has. And that has actually just opened my mind quite significantly on the potentiality that we can come across to discover new other antibiotics or understand the evolution of antimicrobial resistance. And we were managed to put this in a very nice paper I urge you to have a look at. The only thing that I would recognize is my picture. I completely don't understand anything really in that context apart from the microbial familiars that we were able to identify. In short, I just want to walk you through the science communication part that we are really passionate about as well. As I mentioned earlier, one of the very important aspects is actually to be able to communicate the science to the public, to raise their awareness, and to get them engaged in our cause. Yet, unfortunately, the scientific papers that we continually publish are quite difficult to be absorbed. And there is a very important role for social media as well to try and simplify this to the public. So we explored this, and the first question was, is it really worth it? And we have discovered that it's actually social media by itself has very small lifespan, and probably will not be an appropriate tool by itself to raise awareness. Yet, by the use of mainstream media, as well as press releases, we were able, as well as public talks like the one I'm producing here, or visiting schools, we were able to raise awareness as we go. And alongside using sport to raise awareness of antimicrobial resistance through the Superbugs Slayers Polo initiative. We were able to, as we go and play with the team, spread the word of antimicrobial resistance to create an advocacy of more and more passionate individuals who can support the cause of antimicrobial resistance. And more recently, with the very nice support of my dear friend and multi-award-winning filmmaker, Abdurrahman Sundugji, who I have the pleasure of having him with us today, we were also used filmmaking to simplify the science of antimicrobial resistance and the potential discoveries that can happen. And just to try and drag you for tonight's show, I would like to play a 90-second trailer.
المجهول قد يكون مخيف، لكن في نفس الوقت قد يكون مثير وملهم.
Caves are one of the last unexplored side of our planet. So it's very fascinating for me, this aspect, because it's like to go to another planet within our own planet.
أنا بالنسبة لي أعتقد إنه الإكسبلوريشن والاستكشاف هو جزء من الطبيعة البشرية، نابع من أي شخص يحب يستكشف، بحب الفضول، بحب الاستكشاف، بحب المعرفة.
أنا عالم أبحاث وعالم ميكروبات.
بنحاول يكون لنا بصمة في الحد من انتشار الميكروبات المقاومة للمضادات الحيوية.
I'm Francesco Sauro. I'm a geologist, and my specialization is speleology, which is the study of caves.
أحد أهم المغازي لهذه الرحلة الاستكشاف الميكروبي في الكهوف.
في مشكلة كبيرة، فتحة الكهف مسدودة.
I invite you all tonight to come and join us, please, for the show. And the main purpose for this kind of work we're doing is really to inspire the next generation of epidemic detectors, those who would support the cause of antimicrobial resistance and many other infectious diseases that can have, impose a threat on our race. And I'm really delighted when I go through the global action plan to combat antimicrobial resistance. I'm very delighted to see that the work we are passionately doing are aligning with the objectives of the global action plan. Improve awareness, doing surveillance, prevention measures, as well as optimize the use of antimicrobial by developing such rapid diagnostic tests. Here's a quick message by the Director General, or the current Director General of the World Health Organization, Dr. Tedros. It's not working, but probably the video is demonstrating the importance of antimicrobial resistance and the potentiality for it to wipe out humanity. But at the same time, he ended his speech by saying that it's possible to combat the issue of antimicrobial resistance. This is another famous quote by Bill Gates, and I really associate with it. And he said the world needs to prepare for epidemics, pandemics, the same way it prepares for wars. And lastly, before I wrap up, I just want to tell you a quick story. When I visited once the Lindau Nobel Laureate meetings, not as a Nobel Laureate yet, this is very optimistic, but it's basically, I had the pleasure of sharing the stage with Professor Martin Chalfie. And he looked at us, looked on the right-hand side at Francisco, and he said, well, we as humans have still, to date, with the current existing technologies, have the ability to discover new places on planet Earth that never been discovered before. And he looked at me and he said, well, and still we're still able to discover new genetics makeups that never been discovered before. And both are explorations. And with this, I would like to wrap up by acknowledging the significant support that I have received by the government of Saudi Arabia, of course, the several agencies that have supported my research, my team at the University of Queensland, as well as the King Saud bin Abdulaziz University for Health Sciences in Riyadh, and the many funding and collaborators, as well as the mentors who have supported me along this very long journey. And I would like to say thank you. Right on time.
Thank you so much, Hussam, for the insightful talk. And I think he might be taking names for the next expedition. So line up here and let's see who's going to be going for the next cave.
I'll be delighted.
Okay, so questions. Who's going to be the brave one to start the first question here? Okay?
Of course, thank you. Good throw.
Thank you for the interesting information.
Pleasure.
What's the status of the policy of access to antibiotics in Saudi Arabia? Because as you said, within the agriculture industry or with our efforts to raise awareness, if we don't block the easy access to antibiotics, a lot of this work will not give us the outcome.
I had the pleasure of sitting on the National Committee to Combat Antimicrobial Resistance. And one of the actions that I'm very proud of personally, and I'm sure my colleagues are, is actually we have managed to put a ban on the over-the-counter prescription of antibiotics. Despite the fact, I'm really happy about this, and you can test it yourself in any of the community pharmacies that exist. Despite the fact I'm really happy about this, I always remember that we are only trying to maintain the 30% portion of antibiotics that are being utilized in medical sector. And I'm sure that the significant challenge is among the 70%. And with a statement from the Deputy Minister as such, with the acknowledging that it's very difficult to manage, then I'm really concerned. Unfortunately, yes.
Questions? Okay. So I have one of mine.
Please.
Should I be worried about bacteria or viruses right now?
Well,
Or should I be traveling to China?
Right now, the new or the novel coronavirus is of course topical, and it has made it to the newsline. So I think we should be worried about both. Infectious diseases have very dark history to humanity. I think I personally believe that one of the greatest challenges to humanity has always been and will continue to be infectious diseases. Please.
Hand sterilizer things that are everywhere. I mean, I'm assuming that there are some good bugs that we should have it in our system fights. And
there's a lot of, so when we talk about one of the important routes to try to prevent the transmission of bacteria, particularly in healthcare situations, is of course maintaining the hand hygiene. Very important. And for our colleagues at the medical wards, there are practices where they are advised on when to wash their hands as well as use hand sanitizers. The good bacteria that you're referring to as the normal flora, they exist not necessarily on top of the skins, but within the skin. And there's some work that demonstrated actually this bacteria, they would not really be, will be significantly impacted by the consistent wash of the hand. They will continue to grow back to their status. But hand hygiene is a very important way to protect ourselves and for those who are practicing at medical wards, our patients. Thank you.
But if I may ask, I mean, a much clearer question.
Of course.
Is washing hands as good as using the hand sanitizer for regular people, not for people working in the hospitals? Or is there one better than the other, just like?
Well, hand sanitizers from alcohol point of view, it has a very minimal effect. Okay. It would kill the bacteria that exists on the surface in a few seconds, and that's it. And it will become inactive immediately. Okay. So both are probably equal. Okay.
So thank you so much. Oh, we have one last question here. Yes. And yes. And another last question. So two last questions.
So Dr. Hussam, I want to ask you, has this study been implemented on a human being yet, or not? If not, then what's the plan to be implemented and studied on human beings?
Which study, to be precise?
The solutions.
Well, the solutions in general. Okay, there's a good question. It's a good question actually, because now we are taking the One Health approach. We're not really focusing on human only, neither animal only or the environment only. It's a One Health approach to implement all of the solutions on all sectors at the same time. And hence, for example, in Saudi Arabia, with the National Committee to Combat Antimicrobial Resistance, we have representatives from the Ministry of Health, as well as the Ministry of Agriculture, and the Food and Drug Authority, and many others, to do a multi-sectorial effort to do it on One Health aspect. So, thank you.
So my question is, from understanding the mechanism of the antibiotic resistant, do you think it's a good idea to apply that or try to mimic that into the beneficial bacteria like normal flora in order like to improve some production of any biological substance?
So it's an area that is definitely not, I haven't read much about, which is probiotics. So there's a big movement toward the use of probiotics for hopefully to reduce or to take out the unnecessary bacteria. The typical example is Clostridium difficile, which usually takes over the intestines and can colonize and cause very severe infection. And one of the measures that is now being implemented is what's called fecal transplantation. So basically, patients would receive transplantations of feces, basically, from healthy individuals to try and give them the healthy microbiota that can try to establish back and wipe out Clostridium difficile. So yes.
Thank you so much.
A pleasure, of course.
Okay, with that, let's thank Dr. Hussam Zawawi again.
Thank you. Pleasure.
Okay. So, two last announcements. The first one, if you are a student and you are going to be attending the next keynote, which it's obligatory, then you have to go out, register, and come back. So don't forget to do that. Second,